The universe appears stable. Matter holds its shape, stars trace predictable paths, galaxies form vast, luminous structures that seem timeless. Across human history, the sky has looked almost unchanged, reinforcing the idea that the cosmos exists in a kind of quiet permanence. This impression, however, is not a reflection of reality but a limitation of perception. Stability exists only within narrow spans of time. Beyond those spans, everything is in motion, everything is evolving, and everything is temporary. Human understanding is anchored to short durations, lifetimes measured in decades, civilizations in centuries, recorded history in mere thousands of years. Even geological timescales stretching into millions of years begin to strain comprehension. Yet these intervals are insignificant when placed against the true scale of cosmic time. The universe, currently about 13.8 billion years old, has already undergone transformations so vast that entire phases of existence have come and gone long before the emergence of observers capable of recognizing them. And even this immense age represents only an early chapter in a far longer timeline. The present era is defined by structure. Galaxies cluster together in immense filaments, stars burn steadily, and planetary systems form stable environments where complex chemistry can emerge. This is not the default state of the universe, but a temporary condition made possible by specific physical circumstances: abundant hydrogen, active star formation, and relatively dense cosmic regions. These conditions create the illusion of permanence because their changes occur too slowly to be directly perceived. However, the processes driving transformation are continuous and irreversible. Within the Milky Way, hundreds of billions of stars orbit a shared gravitational center, forming a rotating disk of light embedded within a halo of dark matter. From within, this structure appears vast and enduring, yet every component is in motion. Stars drift through the galaxy on independent trajectories, subtly altering the overall structure over millions of years. Constellations, often regarded as fixed patterns, are temporary alignments that gradually distort as stars shift positions. Given sufficient time, no recognizable pattern in the night sky remains intact. Beyond the Milky Way lies a broader cosmic environment filled with other galaxies, each moving according to gravitational interactions and the expansion of space itself. Among them is the Andromeda Galaxy, the nearest large galactic neighbour. Separated by approximately 2.5 million light-years, Andromeda is not stationary. It is moving toward the Milky Way at a velocity of roughly 110 kilometers per second. This motion is not immediately apparent because of the immense distance involved, but it is measurable, and it is inevitable in its outcome. Over a timescale of approximately 4 billion years, these two galaxies will begin to merge. This event will not resemble a collision in the conventional sense. The vast distances between stars mean that direct impacts are exceedingly rare. Instead, gravitational forces will dominate, reshaping both galaxies over hundreds of millions of years. Stellar orbits will be disrupted, gas clouds will compress, and new waves of star formation will ignite. The resulting structure, sometimes referred to as a merged elliptical galaxy, will bear little resemblance to either of its predecessors. This process highlights a fundamental aspect of cosmic evolution. Even the larger structures are transient. Galaxies are not permanent fixtures, but dynamic systems subject to continuous change. Their shapes, compositions, and brightness evolve over time as stars are born and die, as gas is consumed, and as gravitational interactions alter their configurations. The apparent stability of galaxies is a consequence of observing them over extremely short intervals relative to their lifespans. On even larger scales, the universe itself is undergoing a transformation driven by expansion. Space is not static. It is stretching, carrying galaxies away from one another. This phenomenon, first observed through the redshift of distant galaxies, reveals that the universe is not only expanding but doing so at an accelerating rate. The cause of this acceleration is attributed to a poorly understood component known as dark energy, which acts in opposition to gravitational attraction on cosmological scales. As expansion continues, the distances between galaxy clusters increase. Over tens of billions of years, galaxies outside local gravitational groups will recede beyond observable limits. Light emitted from those galaxies will never reach observers, effectively removing them from the visible universe. What remains will be a progressively emptier cosmic landscape, not because matter has disappeared, but because it has become inaccessible. The concept of a visible universe is therefore time-dependent. At present, it includes billions of galaxies, each containing billions of stars. In the distant future, this observable region will shrink dramatically, eventually containing only the remnants of the local galactic group. Any observers existing in that era would have no evidence of a larger universe beyond their immediate surroundings. The broader cosmic structure would be permanently hidden by expansion. Simultaneously, the processes that sustain structure within galaxies are finite. Star formation depends on the availability of cold hydrogen gas, which is gradually depleted over time. As stars form, they convert hydrogen into heavier elements through nuclear fusion. When these stars die, some of that material is returned to the interstellar medium, but not in a form that can fully replenish the original supply. Over billions of years, the rate of star formation declines as the available fuel diminishes. Eventually, the universe will reach a point where new star formation becomes exceedingly rare. Existing stars will continue to shine, but their numbers will steadily decrease as they exhaust their nuclear fuel. Massive stars, which burn brightly but briefly, will disappear first. Smaller stars, particularly red dwarfs, will persist for much longer periods, trillions of years, but even they are not eternal. The era in which stars dominate the universe will come to an end. The current abundance of light is therefore temporary. Stars provide the energy that drives most observable processes, from the illumination of galaxies to the chemical reactions necessary for life. As the stellar population declines, the overall brightness of the universe will diminish. This transition will not occur suddenly, but as a gradual fading, stretching across timescales that far exceed the current age of the universe. At a deeper level, the laws governing physical processes impose constraints on the long-term behavior of the universe. One of the most significant is the second law of thermodynamics, which states that entropy, the measure of disorder in a system, tends to increase over time. This principle implies that energy becomes progressively less available for doing useful work. In the context of the universe, it suggests a future in which all processes that depend on energy gradients will eventually cease. The present era is characterized by low entropy relative to what is possible. Energy is unevenly distributed, allowing stars to shine, galaxies to form, and complex structures to exist. Over time, these gradients diminish, energy spreads out, temperatures equalize, and the capacity for change decreases. The universe moves toward a state of maximum entropy, often described as heat death, in which no further work can be extracted from any system. This outcome is not immediate but unfolds over incomprehensibly long durations. Before reaching that final state, the universe will pass through multiple distinct eras, each defined by the dominant forms of matter and energy. The current stelliferous era, dominated by active stars, is only one phase. It will be followed by periods in which stellar remnants, black holes, and eventually elementary particles define the structure of the cosmos. Each transition represents a reduction in complexity. Structures that once formed naturally become impossible to sustain. Processes that once occurred routinely become rare or cease entirely. The universe does not collapse into chaos, but instead drifts toward uniformity, a state in which differences are minimized and change becomes increasingly unlikely. The perception of permanence arises because these transformations occur over timescales vastly exceeding those of human experience. A star that lives for billions of years appears eternal when observed over decades. A galaxy that evolves over hundreds of millions of years appears fixed when viewed within a single lifetime. However, when placed within the broader context of cosmic time, these entities are revealed to be temporary configurations of matter and energy. The same principle applies to all structures regardless of scale. Planets form and eventually become uninhabitable. Stars ignite and eventually extinguish. Galaxies assemble and eventually disperse. Even the fundamental particles that make up matter may not be stable indefinitely, depending on the validity of certain theoretical models such as proton decay. If such processes occur, then the very concept of matter as a persistent entity is called into question. In this framework, permanence is not a property of the universe, but an emergent illusion created by limited observation. Stability exists only within specific intervals, bounded by the timescales of the processes involved. Beyond those intervals, change is inevitable and continuous. The current moment occupies a unique position within this progression. It exists during a period when the universe is still active, still luminous, and still capable of supporting complex structures. This combination of conditions is temporary and will not be repeated once it passes. The long-term trajectory of the universe leads away from complexity and toward simplicity, away from structure and toward uniformity. What appears stable is therefore already in the process of dissolving, even if the rate of change is imperceptible. The motion of galaxies, the evolution of stars, the expansion of space, and the increase of entropy are all components of a single, continuous transformation. The universe is not static but dynamic, not permanent but transient. The illusion of permanence persists only because the full timeline is not directly observable. When that timeline is extended, when billions, trillions, and beyond are considered, the true nature of the universe becomes clear. Everything that exists does so within a finite window. Every structure has a beginning and an end. Every era gives way to another. The story of deep time is therefore not one of sudden endings but of gradual transitions. The lights do not extinguish all at once, they fade. Structures do not collapse instantly, they evolve and dissipate. The universe does not end abruptly. It changes continuously until change itself becomes impossible. This is the starting point. A universe that appears stable but is already in motion. A cosmos filled with light but destined for darkness. A moment of structure suspended within an infinite progression towards stillness. The next stage in this progression begins with the evolution of stars and the slow transformation of galaxies, where the first major shifts in the long-term fate of the universe become unavoidable. The present universe is defined by light. Across vast distances, galaxies radiate energy produced in the cores of stars, where nuclear fusion converts hydrogen into heavier elements. This process, simple in principle yet immense in scale, is responsible for nearly all visible structure. Stars illuminate galaxies, shape their evolution, and create the conditions necessary for complexity. This era, known as the stelliferous era, is not permanent. It is sustained by a finite resource, and its decline begins long before its end becomes obvious. Within the Milky Way, star formation has already slowed compared to its peak billions of years ago. Regions once dense with cold hydrogen gas have thinned as material has been consumed or heated beyond the conditions required for collapse. Massive stars form, burn intensely and die quickly, returning some of their material to the interstellar medium, but not in a way that fully restores the original balance. Over time, Each generation of stars leaves the galaxy slightly poorer in the raw fuel required for future stars. This gradual depletion is not unique to the Milky Way. Across the observable universe, galaxies are aging. Star formation rates have been declining for billions of years. The brightest, most active period of stellar creation occurred in the distant past, when galaxies were richer in gas and more prone to interactions. Since then, the universe has been entering a long, slow dimming phase. The decline is subtle when measured over short intervals, but across cosmic timescales it is unmistakable. Amid this ongoing change, a significant event approaches. The Andromeda Galaxy, moving steadily through space, continues its approach toward the Milky Way. The separation between these two massive systems decreases with each passing moment, guided by their mutual gravitational attraction. Unlike the general expansion of the universe, which drives distant galaxies apart, gravity dominates at this scale, pulling these two systems together in defiance of cosmic expansion. The initial stages of the encounter begin long before any visible overlap. As the galaxies draw closer, their outer halos, vast regions of dark matter and sparse stars, start to interact. Gravitational forces subtly distort their shapes, stretching and warping the distribution of matter. These distortions grow more pronounced as the distance shrinks, eventually leading to dramatic tidal interactions that reshape both galaxies. When the first close pass occurs, the structure of each galaxy is disrupted. Long streams of stars are pulled outward, forming tidal tails that arc through space. Gas clouds collide and compress, triggering bursts of star formation. These events temporarily reverse the long-term decline in stellar birth rates, creating a brief period of renewed luminosity. The galaxies, once relatively stable, become chaotic environments where gravitational forces dominate every scale. Despite the scale of the interaction, direct collisions between individual stars remain rare. The distances separating stars within galaxies are so vast that even during a merger, most stars pass by one another without direct contact. The transformation is driven not by collisions but by gravity, by the collective influence of billions of stars, gas clouds, and dark matter acting together to reshape the system. Over hundreds of millions of years, the galaxies separate slightly after their first encounter, only to be drawn back together again. Each pass strips more structure, redistributes more matter, and accelerates the process of merging. Eventually, the distinction between the Milky Way and Andromeda disappears. What remains is a single, larger galaxy, an elliptical system with a more randomized stellar distribution and far less organized structure than the spiral galaxies that preceded it. This merged galaxy represents both an end and a beginning. It marks the conclusion of a long period of relative stability for both original galaxies, while also initiating a final phase of significant star formation. The collisions between gas clouds during the merger create ideal conditions for the birth of new stars. For a time, the galaxy becomes brighter than either of its progenitors, filled with young, luminous stars that burn intensely. However, this resurgence is temporary. The same process that creates new stars also accelerates the consumption of the remaining gas. The merger effectively uses up the last significant reserves of star-forming material. Once this gas is exhausted, the rate of star formation declines sharply. The galaxy transitions from a dynamic, star-forming system to a more passive structure dominated by aging stars. The long-term trajectory becomes clear. Without a continuous supply of cold hydrogen gas, new stars cannot form at the same rate as before. The stellar population begins to age collectively. Massive stars, which have short lifespans, disappear first. Their deaths, often marked by supernova explosions, briefly enrich the surrounding space with heavier elements, but do not reverse the overall decline. Intermediate mass stars follow, evolving into white dwarfs after shedding their outer layers. only the smallest stars, red dwarfs, remain for extended periods. Red dwarfs represent the final phase of sustained stellar activity. Their low mass allows them to burn hydrogen extremely slowly, extending their lifespans to trillions of years. During this period, they provide a faint but persistent source of light. However, their dimness means that the overall brightness of the galaxy is significantly reduced compared to earlier eras. The universe, once filled with brilliant, massive stars, becomes dominated by these smaller, cooler objects. As time progresses, even this diminished activity declines. Red dwarfs eventually exhaust their fuel, transitioning into stellar remnants. The era in which stars define the universe begins to close. The transition is gradual, occurring over timescales that far exceed the current age of the universe, but it is irreversible. Each generation of stars reduces the available fuel, ensuring that the process cannot continue indefinitely. Beyond the local galaxy, the larger cosmic context is also changing. The expansion of the universe continues, driven by dark energy. While gravity dominates within the merged galaxy, it cannot counteract expansion on larger scales. Distant galaxies move farther away, their light increasingly redshifted and eventually stretched beyond detectability. Over tens of billions of years, the observable universe shrinks to include only the remnants of the local group, now unified into a single structure. This isolation has profound implications. The merged galaxy becomes effectively alone, surrounded by an expanding void. No new external material enters the system. No interactions with other galaxies occur. The supply of gas is finite and internal, ensuring that once it is consumed, no new source will replenish it. The galaxy evolves in isolation, following a predetermined path toward reduced activity and increased uniformity. Within this environment, gravitational interactions continue to reshape the internal structure. Stars pass near one another, exchanging energy through gravitational encounters. Some are ejected into intergalactic space, becoming isolated wanderers in an increasingly empty universe. Others migrate toward the center, where a supermassive black hole grows by accreting matter and merging with other black holes formed from the remnants of massive stars. Over immense timescales, these processes lead to a gradual redistribution of mass. The galaxy becomes less dense, its structure more diffuse. The once prominent features of spiral arms, dense star clusters, and active star-forming regions fade away. What remains is a quieter, more stable system, composed largely of long-lived stars and stellar remnants. The decline of the stelliferous era is not marked by a single event, but by a continuous reduction in activity. The peak of star formation lies in the past, and every subsequent epoch sees fewer new stars and more aging ones. The balance shifts steadily toward older, dimmer objects. The universe, once vibrant with energy and change, becomes increasingly subdued. At a fundamental level, this transition reflects the finite nature of the processes that generate structure. Nuclear fusion requires fuel, and that fuel is limited. Once consumed, it cannot be fully restored. The energy released by stars drives the evolution of galaxies and the formation of complex systems, but it also ensures its own eventual depletion. The same processes that create structure also lead to its decline. The merging of the Milky Way and Andromeda serves as a focal point within this broader narrative. It is a dramatic event, reshaping entire galaxies and producing a temporary resurgence of activity. Yet it also accelerates the long-term trend toward depletion. By triggering intense bursts of star formation, it hastens the consumption of the remaining gas, bringing the end of widespread stellar activity closer. In this sense, even the most energetic events contribute to the overall decline. Supernovae, starbursts, and galactic mergers all redistribute and consume energy and matter, moving the universe toward a state of lower activity. Each transformation reduces the potential for future change, gradually simplifying the cosmic landscape. As the stelliferous era progresses toward its conclusion, the universe transitions from a state dominated by luminous stars to one defined by their remnants. White dwarfs, neutron stars, and black holes begin to outnumber active stars. The sources of light diminish, and the average temperature of the universe continues to fall. The shift is subtle at first, but becomes increasingly pronounced over time. Eventually, the conditions that define the current universe, abundant light, active star formation, and complex structures, become rare. The processes that once occurred naturally and frequently require increasingly specific conditions, making them less common. The universe moves toward a state where change is slower, less dramatic, and less capable of producing new forms of structure. The era of stars, which once seemed endless, reveals itself to be a temporary phase within a much longer timeline. Its beginning was marked by the formation of the first stars from primordial gas, and its end will be marked by the exhaustion of that gas and the fading of the last stellar light. Between these points lies the period in which the universe is most dynamic, most luminous, and most capable of supporting complexity. The present moment lies within this period, but not at its peak. The universe has already passed its most active phase of star formation. What remains is a gradual decline, punctuated by events such as galactic mergers that briefly reverse the trend but ultimately contribute to it. The overall direction is clear: fewer stars, less light, and a steady movement toward a darker cosmos. This transition does not signify an immediate end, but the beginning of a long descent. The structures that define the current universe will persist for vast spans of time, but their dominance will diminish. The next era will be shaped not by the creation of new stars, but by the evolution of existing ones and the remnants they leave behind. The fading of starlight marks the first major step in the universe's long-term transformation. It is the point at which the most visible and familiar aspect of the cosmos begins to disappear. What follows is a sequence of changes that lead to increasingly sparse and simplified structures, culminating in a universe where light itself becomes rare. The stelliferous era, for all its brilliance and complexity, is only a phase. Its decline is already underway, driven by the same processes that once sustained it. The merger of galaxies, the consumption of gas, and the aging of stars all contribute to a future in which the universe is quieter, darker, and less active. The next stage in this progression emerges as the last stars continue to burn, extending the era of light as long as possible before yielding to the inevitable. The merger between the Milky Way and the Andromeda Galaxy does not end in a single moment, but unfolds across hundreds of millions of years, gradually erasing the identities of both systems. What emerges from this prolonged interaction is not a spiral galaxy, but a far more diffuse and chaotic structure, and Vishal elliptical remnants shaped by repeated gravitational disturbances. The ordered rotation that once defined both galaxies gives way to a randomized distribution of stellar orbits, where stars move in complex intersecting paths rather than in a coherent disk. The night sky, if observed from within this newly formed system, would no longer display the familiar banded structure of a spiral galaxy, but instead a dense, uneven glow stretching in all directions. During the final stages of the merger, the galaxy experiences one last surge of activity. Gas clouds, destabilized and compressed by tidal forces, collapse rapidly under gravity, igniting widespread star formation. This phase, often referred to as a starburst, produces a large population of young, massive stars that burn intensely and briefly. For a relatively short cosmic interval, the galaxy becomes brighter than at almost any point in its history. Radiation floods the surrounding space, and supernova explosions become more frequent as these massive stars reach the end of their short lifespans. The galaxy appears rejuvenated, as though the decline of the stellar era has been reversed. This resurgence is deceptive. The same processes responsible for this temporary brilliance also accelerate the depletion of the remaining star-forming material. Hydrogen gas, the essential fuel for nuclear fusion, is consumed at an unsustainable rate. Each new generation of stars locks away a portion of this fuel in stellar remnants, or disperses it in forms that are less likely to collapse again into new stars. The starburst phase, while visually spectacular, marks the beginning of the final exhaustion of the galaxy's usable resources. As the merger settles and gravitational interactions stabilize, the rate of star formation begins to drop sharply. The galaxy transitions into a more passive state, where few new stars are born. The stellar population becomes dominated by older stars, objects that formed during earlier epochs and are now progressing toward the ends of their life cycles. Massive stars disappear quickly, leaving behind neutron stars or black holes, while intermediate stars evolve into red giants before shedding their outer layers and forming white dwarfs. The overall brightness of the galaxy begins to decline as the most luminous stars vanish. Over billions of years, this process becomes increasingly pronounced. The absence of significant gas reservoirs prevents the formation of new bright stars, ensuring that the galaxy cannot sustain its earlier levels of luminosity. The light that remains is produced by longer-lived, lower-mass stars, which burn more slowly and emit less energy. The spectral character of the galaxy shifts toward redder wavelengths, reflecting the dominance of cooler stars. The once vibrant, multicolored light of a star-forming galaxy fades into a more uniform and subdued glow. This transformation is not unique to the merged remnant of the Milky Way and Andromeda. Across the universe, similar processes occur as galaxies exhaust their gas supplies. Elliptical galaxies, in particular, represent a late stage of galactic evolution, where most star formation has already ceased. These systems are often composed primarily of older stars, with little internal activity to alter their structure significantly. The merged galaxy becomes part of this broader class, a quiet, aging system moving steadily toward a darker future. At the same time, the larger cosmic environment continues to change. The expansion of the universe, driven by dark energy, steadily increases the distances between galaxies that are not gravitationally bound. While the merged galaxy remains intact, it becomes increasingly isolated from all others. Light from distant galaxies is stretched to longer wavelengths, eventually moving beyond the visible spectrum and becoming undetectable. Over tens of billions of years, the observable universe contracts to include only the local structure formed by the merger. This isolation has a profound effect on the long-term evolution of the galaxy. Without incoming material from external sources, the internal supply of gas becomes the only resource available for star formation. Once it is depleted, there is no mechanism to replenish it. The galaxy becomes a closed system, evolving solely through the processes occurring within it. This ensures that the decline in star formation is not only inevitable, but irreversible. Within the galaxy, gravitational interactions continue to reshape the distribution of stars and remnants. Over time, close encounters between stars lead to energy exchanges that alter their orbits. Some stars gain enough velocity to escape the gravitational pull of the galaxy entirely, becoming intergalactic wanderers. Others lose energy and drift toward the central regions, contributing to the growth of a supermassive black hole. This gradual redistribution of mass leads to a more diffuse structure, with fewer dense regions and a more even spread of matter. As the stellar population ages, the nature of the galaxy's light changes further. The brightest stars which once dominated the galaxy's luminosity are no longer present. What remains are smaller, dimmer stars and the faint glow of stellar remnants. White dwarfs, the dense cores left behind by medium-sized stars, contribute a small amount of residual heat and light, but they gradually cool over time. Neutron stars and black holes emit little to no visible light, making them effectively invisible except through their gravitational effects. The decline in brightness is not uniform but follows the life cycles of different types of stars. Massive stars disappear first, followed by intermediate stars, leaving only the smallest stars, red dwarfs, to persist for extended periods. These stars burn their fuel with extreme efficiency, allowing them to shine for trillions of years. During this phase, the galaxy enters a period of prolonged but diminished luminosity, where the overall light output is significantly lower than in earlier eras but still present. Despite their longevity, red dwarfs cannot prevent the eventual fading of the galaxy. Their slow fusion processes mean that they emit relatively little energy, and as they gradually exhaust their fuel, they transition into stellar remnants as well. Over time, the number of active stars continues to decrease, and the balance shifts further toward non-luminous objects. The galaxy becomes increasingly dark, with only scattered points of faint light remaining. Meanwhile, the expansion of the universe continues to isolate the galaxy further. Any remaining external light sources move beyond the cosmic horizon, leaving the galaxy effectively alone in an ever-expanding void. The background radiation of the universe, already faint, becomes stretched to longer wavelengths, reducing its energy and making it more difficult to detect. The environment becomes colder and darker, with fewer sources of illumination. The concept of a typical galaxy begins to lose meaning in this context. With most galaxies no longer observable, and internal activity reduced to minimal levels, the universe appears far less complex than before. The rich diversity of galactic forms, spirals, irregulars, and interacting systems gives way to a small number of isolated aging structures. The merged galaxy, once the product of a dramatic collision, becomes one of many quiet remnants scattered across an expanding cosmos. On the scale of trillions of years, the cumulative effect of these processes becomes overwhelming. Star formation effectively ceases, leaving behind a population of aging stars that steadily transition into remnants. The energy output of the galaxy declines, and its internal dynamics slow as fewer interactions occur. The once vibrant system becomes a static collection of objects, each following its own path through space with little influence on others. At this stage, the universe is still recognizable in terms of familiar structures, galaxies, stars, and remnants. But the balance has shifted decisively away from creation and toward decay. The processes that once generated new structure are no longer active, and the existing structures are gradually breaking down. The direction of change is unambiguous. Fewer stars, less light, and increasing uniformity. The merged galaxy serves as a microcosm of this broader transformation. Its history encapsulates the rise and fall of stellar activity, from the initial abundance of gas and rapid star formation to the final depletion of resources and the dominance of stellar remnants. It illustrates how even the largest and most complex systems are subject to the same fundamental limitations imposed by physics. As time continues, distinction between different types of stellar remnants becomes more important. White dwarfs cool and fade, neutron stars emit diminishing radiation, and black holes persist as the most stable and long-lived objects. The galaxy's mass becomes increasingly concentrated in these remnants, particularly in black holes that grow through mergers and accretion. The luminous component of the galaxy becomes a smaller fraction of its total mass. Eventually, the era defined by active stars gives way to a new phase in which remnants dominate completely. The last sources of sustained light are the smallest, longest-lived stars, whose gradual extinction marks the final transition. Once they're gone, the galaxy no longer produces significant light through nuclear fusion. The universe enters a state where the familiar concept of a shining galaxy no longer applies. The transformation from a bright star-filled galaxy to a dark collection of remnants is not abrupt but continuous. Each stage blends into the next, making it difficult to define precise boundaries between eras. However, the overall trend is clear: a steady decline in activity and luminosity, driven by the consumption of finite resources and the irreversible nature of physical processes. The new galaxy, born from the merger of two large systems, begins as a site of intense activity, but evolves into a quiet, aging structure. Its brightness fades, its internal processes slow, and its role within the larger universe diminishes as that universe expands and isolates it. The light that once defined it becomes increasingly rare, marking the gradual end of the era in which stars dominate the cosmos. What remains is a transition point. The universe has not yet reached darkness, but it is moving steadily in that direction. The final stars continue to burn, extending the presence of light as long as possible, but their numbers are finite, and their lifespans, though immense, are not infinite. The next stage in the evolution of the universe emerges as these last stars begin to define the limits of the stelliferous era, carrying the cosmos toward a future where light itself becomes an exception rather than the rule. As the merged remnant of the Milky Way and the Andromeda Galaxy settles into long-term stability, the universe enters a phase defined not by creation, but by endurance. The conditions that once fueled rapid star formation have largely disappeared. Cold hydrogen gas, the essential ingredient for new stars, has been consumed, dispersed, or locked away in forms that can no longer collapse efficiently. What remains is a finite population of stars, each progressing along a predetermined evolutionary path toward extinction. At this stage, the stellar population is no longer diverse in the way it once was. The most massive stars, which lived fast and died young, have long since vanished. Their lifespans, measured in millions of years, were insignificant even compared to earlier cosmic eras. Intermediate stars have also completed their evolution, leaving behind white dwarfs as silent remnants of their former activity. What dominates now are the smallest stars ever formed, red dwarfs, objects so stable and efficient that they outlive every other type of star by orders of magnitude. Red dwarfs represent the final phase of sustained nuclear fusion in the universe. With masses often less than half that of the Sun, their internal pressures and temperatures are lower, allowing them to burn hydrogen slowly and steadily. Unlike larger stars which exhaust their core fuel relatively quickly, red dwarfs mix their material more thoroughly, ensuring that nearly all of their hydrogen is eventually used. This efficiency extends their lifespans into the trillions of years, far beyond the current age of the universe. During this prolonged era, the universe is dim but not yet dark. The light emitted by red dwarfs is faint and shifted toward longer wavelengths, giving galaxies a deep reddish glow. The brilliance of earlier epochs, marked by bright blue stars and explosive supernovae, is gone. In its place is a quieter, more uniform illumination, steady but subdued. The overall luminosity of the universe declines significantly, but it does not disappear entirely. The distribution of light also changes. Without ongoing star formation, no new luminous regions emerge. The existing stars are spread throughout aging galaxies, their positions determined by long-term gravitational interactions rather than recent formation events. Star clusters gradually disperse, and the boundaries between different stellar populations become less distinct. The universe appears more uniform, with fewer dramatic contrasts between regions of high and low activity. Over trillions of years, even the stability of red dwarfs cannot prevent gradual change. Each star, no matter how efficient, consumes its hydrogen fuel. The process is slow, almost imperceptible on shorter timescales, but it is continuous. As the hydrogen supply diminishes, the internal structure of these stars begins to shift. Fusion rates decrease, luminosity drops, and the stars slowly transition toward their final states. Unlike more massive stars, red dwarfs do not undergo dramatic transformations such as supernova explosions. Instead, they fade quietly. As fusion ceases, they contract slightly and cool, eventually becoming stellar remnants. These remnants, often referred to as helium white dwarfs or similar objects depending on their composition, emit residual heat but no longer generate energy through fusion. Over time, they cool further, transitioning toward complete darkness. This marks a critical threshold in the history of the universe. For the first time, the number of active stars begins to approach zero. The long-lived red dwarfs, once the dominant sources of light, gradually disappear. The universe, which has sustained stellar activity for trillions of years, begins to lose its final natural light sources. The pace of this transition is extremely slow, stretching across immense spans of time. At any given moment, there are still some red dwarfs shining, even as others fade. The decline is not synchronized but staggered, creating a prolonged twilight rather than an abrupt darkness. However, the direction is irreversible. Each extinguished star reduces the total luminosity of the universe, bringing it closer to a state where no fusion-driven light remains. Meanwhile, the larger structure of the universe continues to evolve. The expansion driven by dark energy further isolates the remnants of galaxies. Any light emitted by distant objects is stretched to longer wavelengths, losing energy and becoming increasingly difficult to detect. The cosmic background radiation, already faint, continues to cool, approaching temperatures that make it effectively undetectable by any conventional means. Within the remnants of galaxies, gravitational interactions persist but become less frequent as stellar densities decrease. Encounters between stars and remnants lead to gradual changes in orbital configurations. Some objects gain enough velocity to escape entirely, drifting into intergalactic space where they become isolated from all others. Others fall inward, contributing to the growth of central black holes that continue to accumulate mass over time. These black holes, formed from the remnants of massive stars and the mergers of smaller black holes, become increasingly significant. As the number of active stars declines, black holes represent a larger fraction of the total mass in galaxies. Their gravitational influence shapes the remaining structure, drawing in nearby objects and occasionally merging with other black holes in events that release bursts of gravitational energy. Despite these interactions, the overall level of activity in the universe is diminishing. The absence of new star formation removes one of the primary drivers of change. Without the continuous birth of new stars, the processes that once reshaped galaxies become less frequent and less energetic. The universe transitions from a dynamic system to a more static one, where change occurs slowly and infrequently. As time extends further, the concept of a living universe begins to lose meaning. The processes associated with stellar life, fusion, radiation, and explosive death, become relics of the past. What remains are the aftereffects of those processes: stellar remnants slowly cooling, black holes quietly growing, and particles drifting through an expanding void. The final stages of red dwarf evolution mark the closing boundary of the stelliferous era. This era, defined by the presence of active stars, spans from the formation of the first stars to the extinction of the last red dwarfs. Its duration is immense, covering trillions of years, but it is finite. Once the last star ceases fusion, the universe enters a fundamentally different phase, one in which no new light is generated through nuclear processes. At this point, the universe becomes dominated by remnants. white dwarfs, neutron stars and black holes outnumber any remaining luminous objects. The light that once filled galaxies is replaced by darkness, punctuated only by faint residual emissions. The temperature of the universe continues to decline, and the overall energy available for processes decreases. The transition is not marked by a sudden event, but by the gradual disappearance of the last sources of sustained light. The final red dwarfs, having burned their fuel over trillions of years, fade one by one. Each extinction represents the end of a long-lived system that once contributed to the illumination of the cosmos. When the last of these stars goes dark, the universe crosses a threshold from which it cannot return. The significance of this transition lies not only in the loss of light, but in the end of a fundamental process. Nuclear fusion, which powered the universe's most visible structures, no longer occurs naturally. Without fusion, no new stars can form, and no existing stars can sustain themselves. The universe loses its primary mechanism for generating energy in concentrated observable forms. From this point forward, the evolution of the universe is governed by different processes. The focus shifts from the creation and life of stars to the long-term behavior of their remnants. Cooling, decay, and gravitational interactions replace fusion as the dominant drivers of change. The universe becomes quieter, darker, and more uniform. The last stars, though faint and long-lived, represent the final expression of an era that once defined the cosmos. Their existence extends the presence of light as long as physically possible, but they cannot prevent the inevitable transition. The conditions that allowed them to form no longer exist, and their eventual extinction is a direct consequence of the processes that sustained them. As the final red dwarfs fade, the universe approaches a state where light is no longer a defining feature. The remaining sources of illumination are weak and transient, incapable of sustaining the complexity that once characterized cosmic structures. The transition to the next era becomes unavoidable. What follows is a universe defined not by stars, but by what remains after them. A vast expanse populated by cold, dense remnants, and dominated by the slow, inexorable processes of decay and gravitational interaction. The stelliferous era, once vibrant and full of energy, gives way to a darker, quieter phase in which the legacy of stars continues, but their light is gone. With the extinction of the final red dwarfs, the universe crosses a decisive threshold. The long era defined by active stars comes to an end, not with a sudden collapse, but through a gradual and irreversible fading of light. Nuclear fusion, the process that powered stars for trillions of years, ceases entirely. No new stars are born, and none remain alive. What follows is a fundamentally different phase of cosmic history, the degenerate age, an era dominated not by creation, but by remnants. Every star that once existed has left behind a final state. These remnants now define the structure of the universe. Low and medium-mass stars have become white dwarfs, dense, compact objects roughly the size of Earth, but containing a mass comparable to the Sun. Their matter is supported not by thermal pressure, as in normal stars, but by a quantum mechanical effect known as electron degeneracy pressure. More massive stars have collapsed into neutron stars, where matter is compressed to extreme densities, forming objects only a few kilometers across but containing more mass than entire stellar systems. The most massive stars have formed black holes, regions where gravity is so strong that no light or information can escape. These remnants are fundamentally different from the stars that preceded them. They do not produce energy through fusion, and they do not shine in the conventional sense. Instead, they persist as stable configurations of matter, slowly releasing any residual energy left over from their formation. The universe, once filled with light and continuous activity, becomes a landscape of silent, long-lived objects. White dwarfs are the most numerous of these remnants. Initially, they retain significant heat and emit a faint glow as they radiate away their stored thermal energy. Over immense spans of time, however, they cool. This cooling process is extraordinarily slow, extending over trillions of years. As their temperature drops, their luminosity decreases until they emit almost no detectable radiation. At this stage, they become what are known as black dwarfs, cold, dark objects that no longer produce visible light. In the present universe, none exist, because not enough time has passed. In the degenerate age, they become the dominant form of stellar matter. Neutron stars, though less common, represent another important component of this era. Their extreme density and strong magnetic fields allow them to emit radiation for long periods, especially if they are rapidly rotating. Some exist as pulsars, emitting beams of radiation that sweep through space like cosmic lighthouses. Over time, however, they lose energy, their rotation slows, and their emissions weaken. Eventually, they too fade into near invisibility, detectable only through their gravitational effects. Black holes become increasingly significant as time progresses, formed from the collapse of massive stars or through the merging of smaller black holes. They grow by absorbing matter and by merging with one another. Unlike white dwarfs and neutron stars, black holes do not cool in the traditional sense. They remain as stable concentrations of mass and energy, exerting a powerful gravitational influence over their surroundings. During the degenerate age, they gradually become the dominant repositories of mass in the universe. As these remnants come to dominate, the universe becomes darker and quieter. Without active stars, there is no sustained source of visible light. The faint emissions from cooling white dwarfs and the occasional radiation from neutron stars provide only minimal illumination. The overall brightness of the universe declines dramatically, and the average temperature continues to fall as energy becomes more evenly distributed. Galaxies, once vibrant systems filled with star formation and dynamic processes, undergo a profound transformation. Without new stars to replenish their populations, they become collections of aging remnants. Gravitational interactions continue, but at a much slower pace. Over time, close encounters between objects lead to subtle exchanges of energy that alter their orbits. Some objects gain enough velocity to escape their host galaxy entirely, drifting into intergalactic space as isolated wanderers. Others lose energy and gradually move inward, often towards central black holes. This process, known as gravitational relaxation, leads to the gradual breakdown of galactic structure. Dense regions become less concentrated as objects are scattered, and the distinction between different regions becomes less pronounced. Over extremely long timescales, galaxies lose their clear identities, transitioning from organized systems into diffuse collections of remnants spread across vast distances. Occasionally, rare events disrupt this stillness. Two white dwarfs may collide, triggering a thermonuclear explosion similar to a Type 1a supernova. These events briefly produce intense light in an otherwise dark universe, but they are exceedingly rare due to the immense distances between objects. Neutron star mergers can also occur, releasing bursts of energy and gravitational waves. However, as the universe expands and densities decrease, such interactions become increasingly uncommon. Black holes continue to grow, particularly in the central regions of former galaxies. As remnants drift inward, they may be captured, adding to the mass of these already massive objects. Over time, black holes merge with one another, forming even larger black holes. These mergers release gravitational waves that ripple through space-time, carrying energy away from the system. Despite their intensity, these events become rarer as the universe continues to expand and objects become more widely separated. On timescales of quadrillions of years, the cumulative effects of these processes reshape the universe. Most white dwarfs have cooled into black dwarfs, emitting no visible radiation. Neutron stars have largely ceased their emissions. Black holes dominate the mass distribution, particularly in regions that were once the centres of galaxies. The universe, once filled with light and structure, is now a sparse and dark expanse populated by cold remnants. The expansion of the universe continues throughout this era, driven by dark energy. As space stretches, the distances between objects increase, further reducing the likelihood of interactions. Any remaining large-scale structures drift apart, and the concept of a galaxy becomes less meaningful. What were once tightly bound systems gradually disperse, leaving behind isolated remnants moving through an ever-expanding void. At a fundamental level, the degenerate age is defined by the absence of processes that create new structure. Without star formation, there is no mechanism to generate fresh complexity. The universe is left with the remnants of earlier activity, evolving only through slow processes that redistribute existing matter. The direction of change is towards simplicity and uniformity. Entropy plays a central role in this transformation. Energy, once concentrated in stars and other active systems, becomes increasingly dispersed. Temperature differences diminish, reducing the potential for work and the likelihood of dynamic events. The universe moves steadily toward a state in which change becomes less frequent and less significant. Time itself takes on a different character in this era. With fewer events occurring, the distinction between different moments becomes less pronounced. The universe changes, but it does so gradually, with long periods of near-total inactivity. The dynamic cosmos of earlier eras gives way to a quieter, more static environment, where the passage of time is marked primarily by cooling and the slow drift of remnants. Despite this apparent stillness, the degenerate age is not the final stage of cosmic evolution. The remnants that dominate this era are not truly permanent. White dwarfs continue to cool, neutron stars lose energy, and even black holes are subject to processes that will eventually lead to their decline. The seeds of further transformation are already present, even if their effects will only become significant over timescales far beyond those already considered. The degenerate age represents a midpoint in the long decline of the universe. It is a phase in which the consequences of earlier activity are fully realized, but the ultimate fate of matter and energy has not yet been reached. The universe is no longer defined by creation, but neither has it reached complete stillness. Instead, it exists in a prolonged state of fading, where the remnants of past processes persist while gradually losing their influence. As time continues, the dominance of black holes becomes more pronounced. These objects, more stable and longer-lived than any other remnants, begin to define the structure of the universe in the eras that follow. The fading of white dwarfs into black dwarfs and the quieting of neutron stars leave black holes as the most significant structures remaining. The universe, once bright and filled with activity, has become a shadow of its former self. Light is rare, events are infrequent, and the overall complexity has diminished. Yet the story is not over. The remnants that define this era will themselves evolve, leading to a new phase in which even these atom structures begin to disappear, and the universe moves closer to its ultimate state of darkness and uniformity. By the deep progression of the degenerate age, structure no longer resembles anything familiar from earlier cosmic history. The remnants of galaxies, once dense, luminous systems, have thinned and dispersed under the slow but relentless influence of gravitational interactions and cosmic expansion. What remains is not a universe of galaxies, but a universe of isolated objects, drifting across distances so vast that interaction becomes an exception rather than a rule. The concept of a galaxy, once defined by billions of stars bound together in recognizable forms, begins to dissolve. Over immense timescales, gravitational encounters between remnants, white dwarfs, neutron stars, black dwarfs, and black holes gradually alter their trajectories. Each close pass transfers energy. Some objects gain velocity and escape entirely, flung outward into intergalactic space. Others lose energy and sink toward what were once galactic centers, often ending in capture by massive black holes. These processes, though individually rare, accumulate over quadrillions of years, systematically dismantling every coherent structure that once existed. What was once a dense stellar system becomes a diffuse cloud. What was once a cloud becomes a sparse distribution. Eventually, even that distribution loses cohesion. The remnants spread so far apart that the idea of a shared gravitational identity becomes meaningless. There are no longer galaxies in any practical sense, only widely separated objects moving through an expanding void. Dark energy continues to shape the large-scale behavior of the universe. Its influence ensures that expansion accelerates, stretching space itself and increasing the separation between all unbound objects. Over time, even the remnants that once belonged to the same galaxy become effectively isolated. The distances between them grow so large that light, even travelling for trillions of years, cannot bridge the gap. Each object becomes its own cosmic island, surrounded by emptiness in every direction. In this era, visibility as a concept loses relevance. There are no luminous sources strong enough to illuminate the vast distances between objects. Black dwarfs emit no light. Neutron stars have cooled and ceased meaningful radiation. Only the faintest thermal emissions persist, and even these fade over time. The universe becomes almost entirely dark, not because matter has vanished, but because nothing remains capable of producing significant illumination. Black holes remain as the most influential structures. Their gravitational reach extends far beyond their immediate surroundings, allowing them to capture passing remnants that wander too close. Over immense timescales, this leads to the slow growth of isolated black holes, which accumulate mass through occasional interactions. In regions that were once galactic centers, supermassive black holes may still exist, though even they are increasingly isolated as surrounding matter is depleted. Encounters between objects become extraordinarily rare. The average distance between remnants increases continuously, reducing the probability of collisions or close passes. Where earlier eras were defined by frequent interactions, stellar collisions, supernovae, galactic mergers, this era is defined by absence. Most objects will never encounter another again. Their trajectories, once influenced by dense environments, now carry them through near-empty space indefinitely. Time continues to pass, but it does so without noticeable events. The universe does not become static in a strict sense. Motion persists, expansion continues, but change becomes almost imperceptible. Without interactions, there are no dramatic gutni to mark the passage of time. The difference between one moment and the next becomes negligible, as the large-scale structure remains effectively unchanged over immense durations. Entropy continues its steady rise. Energy becomes increasingly dispersed, with fewer gradients available to drive any form of activity. Temperature differences, once responsible for powering stars and complex systems, diminish further. The universe approaches a state in which no process can extract meaningful work from the environment. The direction of change is always toward greater uniformity, greater simplicity, and less potential for transformation. Black dwarfs, once the cooled remnants of white dwarfs, dominate the population of non-black hole objects. These cold, inert masses drift silently through space, interacting only through gravity. They no longer emit light or heat in any significant way. Their presence is detectable only through their gravitational influence, which itself becomes less relevant as distances increase and interactions decline. Neutron stars, though still present, have largely become inactive. Their rotation has slowed, their magnetic fields have weakened, and their emissions have faded. They persist as dense, compact objects, but their role in shaping the universe diminishes over time. Without radiation or significant interaction, they contribute little beyond their mass. Black holes, by contrast, retain a unique significance. Their ability to capture matter ensures that they remain central to any remaining dynamics. However, even their influence is limited by the increasing isolation of objects. With fewer remnants passing within range, the rate at which black holes grow slows dramatically. Eventually they too become isolated, surrounded by vast regions of empty space with no incoming matter. On timescales extending far beyond quadrillions of years, the cumulative effect of expansion becomes overwhelming. Any remnants not gravitationally bound are carried away from one another at accelerating rates. Even those that were once loosely bound may eventually separate depending on the strength of dark energy and the scale of their interactions. The universe transitions toward a state in which each remaining object is effectively alone. In this context, the idea of a shared universe becomes abstract. There is no longer a connected structure, no network of galaxies or clusters. Instead, there are countless isolated points, each separated by distances so great that they cannot influence one another. The universe becomes a collection of disconnected astit, each following its own path through an ever-expanding void. The absence of light and interaction creates an environment that is fundamentally different from anything that came before. Earlier eras were defined by energy exchange, by processes that transformed matter and produced observable effects. In this era, such processes are nearly absent. The universe persists, but it does so in a state of near-complete inactivity. Despite this, the underlying laws of physics remain unchanged. Gravity continues to act, quantum processes continue to occur, and the expansion of space continues to shape the large-scale structure. The difference lies not in the laws themselves, but in the conditions under which they operate. With matter so widely dispersed and energy so evenly distributed, the opportunities for significant katnai become vanishingly small. The long-term fate of the remnants becomes increasingly tied to the behavior of black holes. As the most stable and long-lived structures, they represent the next phase in the evolution of the universe. While other remnants cool and fade into irrelevance, black holes persist, slowly accumulating mass and dominating the gravitational landscape. However, even this dominance is temporary. The processes that will eventually affect black holes operate on timescales so vast that they lie far beyond the already immense durations considered so far. These processes are subtle, rooted in the principles of quantum mechanics, and they ensure that even the most stable structures are not truly permanent. The universe at this stage can be described as a cosmic ghost, a vast expanse containing the faint traces of what once was. The structures that defined earlier eras have dissolved, leaving behind only isolated remnants that carry the memory of past activity in their composition and distribution. There is no longer a sense of growth or evolution, only a slow drift toward greater emptiness. Time continues, but without events to mark its passage, its significance becomes increasingly abstract. The universe does not end in this era, but it approaches a condition where change is so minimal that the distinction between different moments loses meaning. The progression toward uniformity and inactivity continues, driven by the same fundamental laws that shaped the earlier, more dynamic cosmos. The next transformation will emerge not from the creation of new structures, but from the gradual alteration of those that remain. The remnants that define this era, particularly black holes, will eventually become subject to processes that reduce their mass and alter their nature. These processes, though slow beyond comprehension, will drive the universe toward its next stage, a phase dominated not by matter, but by its gradual disappearance. The universe of ghosts is not the end, but it is a profound transition. It marks the point at which structure, interaction, and light have all but vanished, leaving behind a nearly empty cosmos where only the most fundamental processes continue. What follows is an era in which even these final traces begin to fade, carrying the universe closer to its ultimate state. In the deep stretches of the degenerate age, the universe is no longer defined by the formation of structure, but by the persistence of what remains. White dwarfs, neutron stars, and black holes dominate the landscape, separated by vast distances and surrounded by an expanding emptiness. Yet even these remnants are not truly permanent. Beneath their apparent stability lies a set of processes so slow and subtle that they only become meaningful across timescales far beyond ordinary comprehension. The most fundamental question in this era is not how structures form, but whether matter itself is stable. All known matter is composed of particles, protons, neutrons, electrons, bound together by fundamental forces. For most of cosmic history, these particles have been considered effectively permanent. However, certain theoretical frameworks in particle physics suggest that even protons may not be truly stable. If proton decay occurs, then the very building blocks of atoms are subject to eventual dissolution. Should this process exist, it unfolds at an extraordinarily slow rate. A proton may persist for longer than 10 to the power of 34 years or more, before decaying into lighter particles such as positrons and photons. No direct observation has confirmed this process, but in the context of deep time, even extremely rare events become significant. If protons decay, then all matter composed of atoms, planets, white dwarfs, neutron stars, must eventually disintegrate into radiation and elementary particles. White dwarfs, once considered stable endpoints of stellar evolution, are among the first large-scale structures affected by this possibility. Composed primarily of carbon and oxygen nuclei immersed in a sea of degenerate electrons, they are stabilized by quantum mechanical pressure rather than thermal energy. In the absence of proton decay, they would persist indefinitely, slowly cooling into black dwarfs. However, if proton decay occurs, even these dense remnants are not immune. Over immense timescales, their constituent nuclei would gradually break apart, causing the star to lose mass and eventually dissolve into a diffuse cloud of particles. Neutron stars represent an even more extreme case. Their matter exists in a compressed state where atomic nuclei are effectively crushed together, forming a nearly uniform sea of neutrons. If neutrons are also subject to decay, an extension of the same principle, then even these objects are not permanent. The decay of neutrons would gradually destabilize the star, leading to the release of radiation and the slow erosion of its structure. What was once an object of unimaginable density would eventually disperse into a sparse collection of particles. Black holes, however, stand apart from these processes. Classical physics suggests that nothing escapes a black hole once it crosses the event horizon. For a long time, they were considered the final, unchanging structures in the universe. However, quantum mechanics introduces a subtle correction to this picture. Through a process known as Hawking radiation, black holes are not completely stable. Instead, they slowly emit radiation due to quantum effects near the event horizon, causing them to lose mass over time. This process is extraordinarily slow. A black hole with the mass of a star may take 10 to the power of 67 years to evaporate. Supermassive black holes, such as those found at the centers of galaxies, may persist for up to 10 to the power of 100 years or more. During most of the degenerate age, this effect is negligible. Black holes appear effectively permanent, growing through occasional mergers and the absorption of nearby matter. Yet in the deepest timescales, even they are subject to gradual evaporation. The combination of these processes, proton decay, neutron instability and Hawking radiation, introduces a profound shift in the long-term fate of matter. What once appeared stable on all practical timescales is revealed to be temporary when viewed across the full span of cosmic time. The universe is not only evolving toward emptiness through expansion and entropy, but also through the internal instability of its most basic components. As these processes unfold, the large-scale structure of the universe continues to degrade. Galaxies, already dispersed into diffuse collections of remnants, lose coherence entirely. Without stable matter to bind them, gravitational structures weaken. Objects that were once part of organized systems become increasingly isolated. The distinction between galaxy, intergalactic space, and void fades as matter itself becomes sparse and fragmented. White dwarfs and neutron stars, if proton decay is real, gradually lose their integrity. Their mass decreases as particles decay into lighter forms. Over immense timescales, they cease to exist as coherent objects, leaving behind only low-energy radiation and fundamental particles. The universe becomes increasingly dominated by diffuse fields of particles rather than structured bodies. Even in the absence of proton decay, a similar long-term trend emerges. White dwarfs simply cool until they emit no detectable radiation. Neutron stars lose rotational energy and magnetic fields, becoming inert. In both cases, the universe trends toward a state where structure persists only through gravitational binding, and even that becomes less effective as distances increase. Black holes remain the final significant structures. Their ability to concentrate mass and energy ensures that they dominate the last remaining organized regions of the universe. However, Hawking radiation guarantees that they are not eternal. As they emit radiation, they slowly lose mass. The process accelerates toward the end of their lifespan, causing the final stages of evaporation to occur rapidly compared to their earlier history. When a black hole reaches its final phase, it emits a burst of radiation before disappearing entirely. This event briefly introduces energy back into the universe, but it does not reverse the overall trend. The universe continues its progression toward lower energy density and greater uniformity. Once the last black hole evaporates, no large-scale gravitational structures remain. At that point, the universe consists primarily of low-energy particles and radiation. Photons, neutrinos, electrons and positrons drift through an expanding space, their energy steadily decreasing as the universe expands. The temperature approaches absolute zero, not in a strict thermodynamic sense, but as a limit where no meaningful energy differences remain to drive processes. The concept of matter itself becomes increasingly abstract. Without stable atoms, there are no structures in the traditional sense. Without structures, there are no systems, no objects, and no environments. What remains is a dilute sea of particles moving through an ever-expanding void, with no interactions capable of producing complexity. Entropy plays a defining role in this transformation. As energy becomes more evenly distributed, the ability to perform work diminishes. Processes that once required small energy differences become impossible. The universe approaches a state of maximum entropy, where no further increase in disorder is possible because no gradients remain to drive change. Time continues, but its meaning becomes less connected to events. Without processes to mark its passage, time becomes an abstract parameter rather than a sequence of changes. The universe does not experience moments in the way earlier eras did, because there are no longer events to distinguish one moment from another. The slow collapse of matter is therefore not a collapse in the conventional sense, but a gradual unravelling. Structures do not fall inward or explode outward, they simply cease to exist as their components decay, evaporate, or drift apart. The universe transitions from a state of structured complexity to one of diffuse simplicity. Throughout this process, the laws of physics remain unchanged. Gravity, quantum mechanics, and relativity continue to operate, but their effects become increasingly subtle as the conditions required for significant interactions disappear. The universe does not break its rules. It evolves into a state where those rules produce minimal observable consequences. By the end of this phase, nearly all recognizable forms of matter have disappeared. What remains is a universe dominated by low-energy radiation and fundamental particles, scattered across vast distances. Even these particles are subject to further redshift and dilution as expansion continues. The slow collapse of matter represents a critical transition in cosmic history. It marks the point at which the universe loses not only its luminous structures, but also its material foundation. The remnants of stars, planets, and galaxies are gradually erased, leaving behind only the most fundamental components of reality. What follows is a universe stripped of structure, where even the concept of object loses meaning. The next phase moves beyond matter entirely, focusing instead on the behaviour of radiation, black hole remnants, and the final processes that govern an increasingly empty cosmos. After the collapse of matter into increasingly unstable and sparse remnants, the universe undergoes a final structural transition. The degenerate age, defined by the persistence of white dwarfs, neutron stars, and the gradual decay of matter, gives way to a new dominant regime. In this phase, virtually all remaining large-scale structure is governed by a single class of objects: black holes. Black holes are no longer rare endpoints of stellar evolution. They have become the central repositories of mass in the universe. Every massive star that once existed has already collapsed into one, and many smaller black holes have merged over incomprehensible spans of time. The result is a universe where black holes are not anomalies, but the primary gravitational structures around which all remaining matter is organised. Most galaxies, long since transformed into diffuse distributions of remnants, have their mass concentrated into central supermassive black holes. These objects, formed through repeated mergers and accretion during earlier eras, now dominate their local regions entirely. Surrounding them is a vast, thinning halo of cold remnants, black dwarfs, neutron stars, and scattered particles, slowly being drawn inward over time. The black hole era begins when these objects effectively outlast all other forms of long-lived structure. White dwarfs have cooled into darkness. Neutron stars have lost their energy and rotational stability. Matter itself, if unstable, has largely decayed into radiation or elementary particles. What remains are black holes, isolated and widely separated, each representing a gravitational island in an expanding cosmic sea. Despite their apparent simplicity, black holes are not static objects. They continue to interact with their environment, albeit extremely slowly. Matter that drifts too close is consumed. Other black holes may merge, releasing bursts of gravitational waves that propagate through space-time. These events are among the most energetic remaining processes in the universe, but they become increasingly rare as distances grow and available material diminishes. Over time, even the supply of matter feeding black holes is exhausted. The surrounding environment becomes too sparse to sustain significant accretion. Black holes enter a long period of relative isolation during which their mass remains largely constant. They no longer grow significantly through external interactions, and their evolution becomes dominated by internal quantum processes rather than classical gravitational dynamics. The most important of these processes is Hawking radiation. According to quantum field theory and curved spacetime, black holes are not completely stable. Near the event horizon, quantum fluctuations produce particle-antiparticle pairs, some of which result in a net loss of mass from the black hole. Over extremely long timescales, this effect causes black holes to slowly evaporate. For most of cosmic history, Hawking radiation is negligible. A stellar mass black hole takes around 10 to the power of 67 years to evaporate completely, while supermassive black holes at galactic centers may persist for 10 to the power of 100 years or more. During earlier eras, this process is entirely irrelevant compared to accretion and mergers. But in the black hole era, when no significant external matter remains, evaporation becomes the dominant process governing the evolution of the universe's last major structures. As black holes lose mass, their temperature increases. This leads to an acceleration of the evaporation process. The smaller a black hole becomes, the faster it radiates energy. For most of its lifetime, the process is slow and nearly imperceptible. In the final stages, however, it becomes rapid, culminating in a final burst of high-energy radiation before the black hole disappears entirely. This final burst is one of the last significant energetic events in the universe. It briefly releases a concentrated pulse of energy into an otherwise dark and dilute cosmos. However, it does not reverse the overall trend. The universe continues to expand, and the energy released is quickly diluted across vast distances. No lasting structure is formed from these events. As black holes evaporate one by one, the universe transitions toward a state with fewer and fewer gravitational anchors. The largest supermassive black holes are the last to remain. They dominate their regions for the longest periods, slowly consuming the remnants of their environments before finally entering their evaporation phase. When the last of these objects disappears, the universe loses its final significant sources of structure and energy concentration. During this era, the concept of locality begins to lose meaning. In earlier epochs, black holes were embedded within galaxies, which were themselves part of larger cosmic structures. Interactions occurred at multiple scales: stars within galaxies, galaxies within clusters, clusters within filaments. In the black hole era, these hierarchies have collapsed. Each black hole exists in near total isolation, separated by distances so vast that no interaction between them is possible on meaningful timescales. The expansion of space plays a crucial role in this isolation. Driven by dark energy, the universe continues to stretch, increasing the separation between all unbound objects. Over time, even black holes that were once part of the same gravitational system are carried beyond each other's reach. The observable universe from the perspective of any individual black hole becomes increasingly empty, eventually containing nothing but its own event horizon and the faint remnants of distant radiation. Within this environment, black holes represent the final stage of organized structure. They are the most stable configurations allowed by known physics, characterized only by mass, charge, and angular momentum. All other information about the matter that formed them is hidden behind the event horizon. In this sense, they are simple objects, but their simplicity masks an immense complexity of history. As time progresses further, even these final structures begin to lose their dominance. The rate of evaporation eventually exceeds any remaining processes of accretion or merger. Black holes shrink steadily, emitting more radiation as they do so. The universe becomes increasingly dominated by this faint, diffuse radiation rather than by massive objects. When the last black hole evaporates, the universe enters a fundamentally different phase. No gravitationally bound structures remain. No objects exist with sufficient mass to significantly influence their surroundings. The universe becomes a dilute field of particles and radiation, expanding without any internal structure capable of organizing it into distinct forms. This transition marks the end of the black hole era. It is not a sudden event, but the culmination of a process that has been unfolding for trillions upon trillions of years. The disappearance of the last black hole is symbolic rather than disruptive. It does not alter the trajectory of the universe, but confirms its direction. What follows is a universe stripped of nearly all complexity. Radiation dominates, composed of photons stretched to extremely long wavelengths by the continued expansion of space. Elementary particles drift freely, interacting only rarely, their energies steadily decreasing. The universe becomes increasingly uniform, with no regions significantly different from any other. The absence of black holes removes the final mechanism by which matter and energy could be concentrated. Without them, there are no gravitational wells capable of collecting diffuse particles. Everything becomes evenly distributed over time. The universe approaches a state of maximal entropy, where all energy differences have been erased. Even the concept of time becomes less meaningful in this context. Without events, interactions, or structures, there are no processes to distinguish one moment from another. The universe continues to evolve mathematically, but not dynamically in any observable sense. Change becomes so minimal that it is effectively indistinguishable from stasis. The black hole era therefore represents the final chapter in which recognizable structures exist. It is the last period in which the universe contains objects that can be identified, measured, and compared in meaningful ways. Once it ends, the universe no longer contains anything that fits the definition of an object in the classical sense. What remains is a transition into complete uniformity. The universe is not yet finished, but it has reached a point where all major structures have been dismantled. The next stage is defined not by the existence of objects, but by their absence, an era in which only radiation, particles, and the slow expansion of space persist. The story now moves toward its final transformation, where even these remnants lose their significance, and the universe approaches a state of ultimate equilibrium. With the evaporation of the last large black holes, the universe loses its final long-lived gravitational structures. What follows is not an abrupt change in appearance, but a shift in principle. For the first time in cosmic history, there are no objects capable of dominating their surroundings through gravity. Everything that once concentrated mass, energy, and information has either decayed, dispersed, or evaporated. Yet even in this near-uniform cosmos, black holes leave behind a final mechanism that defines the transition into the deepest future: Hawking radiation. Black holes, once thought to be perfectly stable, are not entirely black. Quantum mechanics reveals that empty space is never truly empty. It is filled with fluctuating fields, where particle-antiparticle pairs constantly appear and vanish. Near the event horizon of a black hole, these fluctuations behave differently. One particle can fall in while the other escapes, resulting in a net loss of mass from the black hole. Over extremely long timescales, this process causes black holes to slowly radiate energy and shrink. This discovery fundamentally alters the understanding of the universe's final stages. It means that even the most stable structures allowed by classical gravity are not eternal. Instead, they are temporary reservoirs of mass and energy, destined to slowly evaporate into radiation. For most of cosmic history, Hawking radiation is negligible. A black hole formed from a star takes around 10 to the power of 67 years to evaporate. Supermassive black holes at galactic centers persist for far longer, reaching lifetimes on the order of 10 to the power of 100 years or more. During earlier eras, these timescales are irrelevant compared to the active processes of star formation, galactic evolution, and matter interactions. But in the black hole era, when no significant accretion remains, evaporation becomes the dominant process. As black holes lose mass, their temperature increases. This creates a feedback loop. Smaller black holes radiate faster, which causes them to shrink further, increasing their temperature again. For most of their existence, this effect is extremely slow and stable. However, in the final stages of evaporation, it accelerates dramatically. The last phase of a black hole's existence is characterized by an intense burst of radiation. As its mass approaches zero, its temperature rises sharply, leading to a rapid release of energy in the form of high-energy particles and photons. This final explosion is brief on cosmic timescales, but extraordinarily energetic relative to the surrounding environment. It represents the last moment in which a single object can release a concentrated output of energy into the universe. After this final burst, the black hole disappears entirely. No remnant remains. Its mass has been fully converted into radiation, distributed across an ever-expanding space. This marks the end of the black hole's role as a structure in the universe. With the evaporation of the last black hole, the universe enters a radically different state. No gravitationally bound objects remain at large scales. The universe is no longer structured by mass concentrations. Instead, it is dominated by low-energy radiation and a sparse distribution of elementary particles. Photons, the carriers of electromagnetic radiation, become the most common form of energy. However, as space continues to expand, their wavelengths are stretched. This redshifting reduces their energy over time, causing them to become increasingly faint and difficult to detect. Neutrinos, nearly massless particles that rarely interact with matter, also persist, drifting through space almost entirely unaffected by anything else. Electrons and positrons, if still present in significant numbers, eventually annihilate each other when they encounter. This process converts their mass into additional photons, further increasing the dominance of radiation over matter. Over time, most particle-antiparticle pairs have already annihilated, leaving behind a highly diluted universe of low-energy particles. The absence of black holes removes the last significant source of gravitational structure. Without them, there are no centers around which matter can accumulate. All remaining particles move freely, influenced only by the expansion of space and occasional weak interactions. The universe becomes increasingly homogeneous. At this stage, the concept of objects begins to lose meaning entirely. In earlier eras, objects could be defined as bound systems: stars, planets, galaxies, black holes. Each had internal structure and distinct boundaries. In the post-black hole universe, such definitions no longer apply. Everything is dispersed. There are no stable configurations that persist long enough to be considered objects in the traditional sense. The universe is now dominated by radiation fields and isolated particles, each separated by vast distances. Interactions between them become exceedingly rare. As expansion continues, even the probability of two particles encountering one another approaches zero. The universe becomes not just empty of structure, but empty of meaningful interaction. Despite this, the universe does not stop evolving. The expansion of space continues, driven by dark energy. This expansion increases the distances between all particles and stretches the wavelengths of all radiation. Over time, energy densities decrease further, and the universe moves toward a state of extreme dilution. The final bursts of black hole evaporation introduce temporary disturbances in this uniformity, but these are quickly absorbed into the background. Each event adds energy to the radiation field, but that energy is rapidly spread across an ever-growing volume of space. No lasting structures emerge from these events. In the absence of black holes, the universe loses its last mechanism for concentrating energy. Everything becomes diffuse. the contrast between regions of space diminishes until it becomes effectively non-existent. There are no longer dense or empty regions in any meaningful sense, only variations that are stretched out and diluted beyond significance. Time continues to pass, but without events to mark its progression, its meaning becomes abstract. In earlier eras, time was defined by change, the fusion of stars, the collision of galaxies, the evaporation of black holes. In this era, change becomes so rare that it no longer provides a meaningful measure of temporal passage. The universe evolves, but it does so without observable milestones. Entropy reaches an extremely high level during this phase. Energy is distributed almost uniformly across the universe. Temperature differences are minimal. There are no gradients large enough to drive significant processes. The universe approaches a state of thermodynamic equilibrium, where no further useful work can be extracted from any system. However, even this is not the final state. Quantum fluctuations continue to exist. Particles still appear and vanish in accordance with the uncertainty principle. Space itself retains a dynamic quality at microscopic scales. But these processes do not lead to the formation of structure or the emergence of complexity. They are background activity without macroscopic consequence. The Hawking radiation era represents the final phase in which energy is actively released from structured objects. Once black holes have fully evaporated, no further large-scale energy sources remain. The universe transitions from one defined by the decay of structures to one defined by the absence of structures altogether. What follows is a universe composed almost entirely of low-energy radiation and sparse particles, expanding without limit. The last traces of concentrated energy have been dispersed. The final leaks from black holes have completed their role in cosmic evolution. The significance of this stage lies in its finality. Black holes were the last objects capable of organizing matter and energy into distinct, long-lived forms. Their evaporation removes the final anchor points of structure. After this point, the universe is no longer shaped by objects, but only by fields and background processes. The transition into the next era is therefore not marked by a dramatic event, but by completion. A process that began with the formation of the first black holes ends with their disappearance. In between, they served as the final repositories of structure in a universe steadily moving toward uniformity. With their absence, the universe is no longer divided into regions of meaningful difference. Everything becomes part of a single, expanding, cooling field of radiation. The stage is set for the final transformation, a universe without structure, without objects, and without processes capable of creating change. The next chapter marks the transition into that ultimate state, the final void, where even the faint echoes of structure have faded into uniform darkness. With the complete evaporation of the last black holes, the universe crosses its final structural boundary. No objects remain that can be meaningfully described as gravitational anchors, energy sources, or long-lived concentrations of matter. What follows is not a new era of transformation, but a slow convergence toward uniformity so extreme that change itself becomes nearly meaningless. The universe at this stage consists primarily of low-energy radiation and a sparse background of elementary particles. Photons dominate, having been released over trillions upon trillions of years through the decay of earlier structures, including black holes and residual matter, antimatter annihilations. These photons are no longer energetic in any meaningful sense. As space continues to expand, their wavelengths stretch further, reducing their energy toward absolute minimal values. Neutrinos also persist, passing through space almost entirely without interaction. Their weakly interacting nature allows them to travel across cosmic distances without being absorbed or altered. Electrons and positrons, if any remain, are so widely separated that encounters are extraordinarily rare. When they do occur, annihilation produces additional photons which immediately join the ever-expanding radiation background. The universe is now devoid of structure. There are no galaxies, no stars, no remnants, and no black holes. What remains is a nearly uniform distribution of particles and radiation spread across an immense and continuously expanding volume of space. The concept of location loses its practical meaning, as no region differs significantly from any other. Expansion, driven by dark energy, continues to dominate the large-scale behavior of the cosmos. Space itself stretches without bound, increasing the distances between all particles. Even particles that were once relatively close are carried apart over time, reducing the likelihood of interaction to near zero. The universe does not contract or stabilize, it expands indefinitely, ensuring that any remaining energy becomes ever more diluted. In this environment, temperature becomes an increasingly abstract concept. Without significant energy differences between regions, there is no meaningful heat flow or thermodynamic activity. The universe approaches a state often described as maximum entropy, where energy is distributed as evenly as possible and no gradients remain to drive processes. However, this state is not perfectly static. Quantum mechanics ensures that fluctuations continue to occur at microscopic scales. Virtual particles appear and vanish in accordance with the uncertainty principle. Fields fluctuate locally, even in the absence of macroscopic structure. These processes introduce a form of background activity, but they do not produce lasting change or organized complexity. The absence of structure has profound implications for the concept of time. In earlier eras, time was defined by change, stellar evolution, orbital motion, galactic collisions, black hole evaporation. Each process provided a natural clock by which the passage of time could be measured. In the final void, no such processes exist at macroscopic scales. Time continues as a parameter in physical equations, but it loses any connection to observable events. Without events, there is no distinction between one moment and another. The universe evolves mathematically, but not dynamically in any meaningful sense. Changes in particle distribution or radiation density become so subtle that they are effectively indistinguishable from stasis over any finite observational period. As expansion continues, even the residual radiation becomes increasingly diluted. Photons are stretched to wavelengths so large that their energy approaches zero. In the limit of infinite expansion, the universe trends toward a state where radiation exists but carries no usable energy. This is not a collapse, but a dilution, an infinite spreading of finite energy across infinite space. Particles similarly become more isolated over time. The probability of interaction between any two particles decreases steadily as distances increase. Eventually, the universe becomes so sparse that interactions effectively cease entirely. Each particle becomes an isolated entity, drifting through a vast and expanding void without any possibility of contact. At this stage, the universe is no longer structured in any conventional sense. There are no systems, no environments, and no processes capable of generating complexity. The distinction between matter and space becomes blurred, as both are uniformly distributed and equally devoid of structure. Entropy has reached an extreme level. The universe contains no usable energy gradients, no organized systems, and no mechanisms for reducing disorder. However, this does not imply a true end. Instead, it represents a state of thermodynamic equilibrium on a universal scale, where no further macroscopic change is possible because no differences remain to drive it. Despite this apparent stillness, the universe is not entirely static. Quantum fluctuations continue, and space itself retains a dynamic character at the smallest scales. However, These processes are isolated and do not accumulate into larger structures. They represent noise without consequence, activity without direction. In this final void, even the concept of isolation becomes relative. With no structures to compare, no interactions to observe, and no reference points to define distance or time, the universe becomes a uniform field of near-nothingness. Everything that once existed has been reduced to its most fundamental components, dispersed across an ever-expanding continuum. The remnants of black hole evaporation, the last significant energetic events in the universe, have long since been absorbed into this background. Their energy, once concentrated and meaningful, has been stretched and diluted to the point of irrelevance. No trace of their existence remains in any observable form. What persists is a universe without structure, without complexity, and without direction. It is not empty in the absolute sense, as quantum fields and particles still exist, but it is empty in every meaningful macroscopic sense, devoid of object systems and processes capable of producing change. The final void is therefore not an event but a condition. It is the end state toward which all earlier eras have been moving. The stelliferous universe of stars, the degenerate universe of remnants, the black hole-dominated universe, and finally the radiation-filled aftermath of their evaporation. Each stage reduces complexity, concentrates less energy, and increases uniformity. Now that trajectory reaches its limit. The universe continues to exist, but it no longer evolves in any meaningful way. Expansion persists, particles drift apart, and radiation fades. But no new structures form, and no significant interactions occur. The universe has reached a state where change is no longer a defining feature. What remains is duration without development, existence without differentiation, and time without events. The final void is not an ending in the traditional sense. It is the completion of a long transition from complexity to uniformity. It is the end point of every process that began with the first stars, continued through galaxies and black holes, and concluded with the evaporation of the last massive structures. The universe in this state does not die. It simply ceases to be dynamic, and in that stillness, the long story of cosmic evolution reaches its final form, a universe that still exists, but no longer changes in any way that can be observed, measured, or meaningfully defined. In the final void, the universe no longer contains structures capable of change in any meaningful sense. What remains is a dilute, expanding field of radiation and isolated particles spread across a space-time that continues to stretch without limit. No galaxies persist, no remnants of stars survive in any recognizable form, and even black holes have long since evaporated. The physical ingredients of earlier cosmic eras still exist in principle, but they are so widely dispersed and so low in energy that they no longer participate in processes that create complexity. At this stage, the universe is defined by absence rather than presence, absence of structure, absence of interaction, and absence of gradients that could drive transformation. The laws of physics still operate, but their consequences are minimal. Without energy differences, there are no mechanisms for sustained change. Without interactions, there are no systems. Without systems, there is no evolution in the traditional sense. Radiation dominates what remains of the cosmos. Photons, stretched to extreme wavelengths by continuous expansion, fill space in a nearly uniform distribution. Their energy approaches zero as their wavelengths grow larger and larger, redshifting beyond practical detectability. Neutrinos continue to pass through space, largely unaffected by anything else, their weak interactions ensuring they remain isolated. Electrons and positrons, if any remain, are so widely separated that their encounters are statistically negligible on any finite timescale. Space itself continues to expand, driven by dark energy. This expansion is not a motion through space, but a stretching of space itself, increasing the distances between all unbound particles. Over time, even particles that were once relatively close become separated by distances so vast that no signal, no force, and no influence can bridge them. The universe does not collapse or stabilize. It stretches indefinitely, increasing isolation at every scale. In this environment, the concept of object loses its meaning entirely. Objects require cohesion, structure, and interaction between components. In the final void, none of these conditions exist. There are no bound systems, no persistent configurations, and no mechanisms that could maintain organization. What remains are individual particles and radiation quanta, each effectively isolated from all others. Time, as a parameter in physical equations, continues to exist. However, its connection to observable change has effectively disappeared. In earlier eras, time was measured by events, stellar life cycles, orbital motions, galactic mergers, black hole evaporation. Each provided a reference point that gave time physical meaning. In the final void, such reference points no longer exist. The universe evolves mathematically, but not in a way that produces distinguishable moments. Without events, time becomes indistinguishable from stasis. The equations of physics may still include a temporal variable, but there is no physical process that allows different moments to be compared. The universe no longer changes in any operational sense. It simply exists in a state where change is no longer detectable. Entropy, already maximized in previous eras, remains at an extreme level. Energy is distributed as uniformly as possible, given the constraints of expansion and quantum mechanics. There are no gradients large enough to drive processes, no differences in temperature or density that could lead to flow or transformation. The universe has reached a state of near-perfect equilibrium. Quantum fluctuations continue at microscopic scales, as they must according to the uncertainty principle. Virtual particles appear and vanish, fields fluctuate locally, and space-time retains a subtle dynamism at the smallest levels. However, these fluctuations do not accumulate into larger structures. They remain isolated, random, and without consequence. They represent activity without outcome. As expansion continues, even the residual energy of radiation becomes increasingly diluted. Photons are stretched to wavelengths so large that their energy approaches an infinitesimal limit. In an infinite future, the universe trends toward a state in which radiation exists but carries no practical energy content. It is present in form but absent in function. Particles drift apart without ever encountering one another. The probability of interaction between any two particles becomes so small that for all practical purposes, interactions cease entirely. Each particle becomes an isolated entity in an expanding void, disconnected from all others by distances that grow without bound. The universe, once structured into galaxies, stars, and complex systems, has become a uniform expanse of near nothingness, not absolute nothingness, since fields, particles, and space-time remain, but a state in which no macroscopic distinction exists anywhere. There are no regions of density, no gradients of energy, no structures of any kind. In such a state, the concept of meaning itself becomes difficult to define. Meaning in a physical sense arises from relationships, interactions, and differences. It depends on systems that evolve, respond, and change. In the final void, none of these conditions are met. The universe does not support processes that could generate distinctions or narratives. It simply continues in a state of uniform existence. Even the idea of observation becomes irrelevant. observation requires interaction between systems, exchange of information, and the ability to distinguish states. In a universe where particles are isolated beyond interaction range and energy differences are negligible, observation cannot occur in any meaningful sense. There is nothing to observe and no mechanism by which observation could influence anything. The long history of cosmic evolution, from the formation of the first stars to the evaporation of the last black holes, leads to this condition not through sudden collapse, but through continuous reduction. Each era removed a layer of complexity. Stars introduced structure, galaxies organized matter, black holes concentrated energy. Their eventual disappearance removed the last sources of dynamic change. What remains is a universe that still exists, but no longer participates in processes that create or sustain meaning as understood through physical interactions. It is not destroyed, but it is emptied of the conditions required for significance to arise within it. Time may extend indefinitely into this state, but without events, it loses any operational meaning. The distinction between 1 trillion years and another becomes irrelevant, as nothing changes between them. The universe becomes a static solution to dynamic equations, formally evolving in description, but not in observable consequence. The end of meaning is therefore not an event, but a realization of conditions. It is the point at which the universe no longer supports the structures necessary for difference, interaction, or evolution. It is the final outcome of a process that began with intense energy and complexity and ended in uniform dilution. Yet even here, existence persists. The universe is still described by physical laws, fields still exist, particles still exist, space-time still exists. But their arrangement no longer gives rise to anything beyond themselves. The story of cosmic evolution, when traced across its full depth, leads not to a dramatic conclusion, but to a quiet dissolution of structure. From galaxies to stars, from stars to remnants, from remnants to radiation, and finally from radiation to uniformity, each stage reduces complexity until only the most fundamental components remain.